Welcome, students. We want to now extend the ideas from second order differential equation to nth order differential equations. So, the ideas and methods of second order linear differential equations extend directly to the nth order linear differential equation. So, first of all, what is an nth order linear differential equation? So, an nth order linear differential equation will have an nth order derivative in it. So you see you have an nth order derivative, then all the consequent derivatives. So n minus 1 derivative, blah, 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 all the way until y of t, and that is equal to g of t. So this is called an nth order derivative. Now, when does it becomes linear? It becomes linear if the coefficient of these derivatives are functions of t only. That means they do not have any y terms in them. So a general solution to a to an nth order differential equation of this form will involve n arbitrary constants. And to solve those n constants, if you are given the values at n different values, that is y of t naught equals to y naught, y prime of t naught equals to y naught prime, and so on, then you can solve and get a unique solution. Okay. So because when you do this, you'll get system of equations with n equations with n unknowns, and you'll get a linear system and you'll be able to solve it. So let's discuss the uniqueness and existence of theorem. So before we go there, recall the theorem we had in, so theorem 4.1.1 in page 169. Now this theorem was about second order differential equation, second order linear differential equation. And the question was, does the solution exist and is it unique? So let me rewrite that theorem. So suppose you're given y double prime plus p of ty prime plus q of ty equals to g of t, and you're given an interval I, and pt, qt, and g of t are continuous on I with what else is given to you. So you're given y of what? We are given basically with t naught belonging to I. Then there is a unique solution that satisfies DE with y prime, y of t naught equals to y naught, and y prime of t naught equals to y naught prime. Yeah, this is not derivative of this guy. This is just some other number, y naught prime. So it tells you, so the uniqueness is also consequence of initial value problem. Okay, so you should be given the initial value to determine it uniquely. Now let's generalize this case for nth order differential equation. So we have the following. We have this nth order linear differential equation. So what should happen here? We to have existence and uniqueness, we needed p of t, q of t, and g of t to be continuous. So we can we can extend this naturally then. So if p1t, p2t, dot dot dot, pnt, and g of t are continuous on interval I, with, so continues on interval I with t naught belonging to I, then there exists a unique solution to the differential equation. Which differential equation we are talking about? We are talking about this differential equation here. Yeah, we are talking about this differential equation. Okay, so we're talking about this differential equation. So we say that this differential equation has a unique solution with given satisfying the initial set of conditions. So it has unique solution to differential equation star satisfying y of t naught equals to y naught, y prime of t naught equals to y naught prime, so on, so forth, and yn minus t naught equals to some y naught. Yeah, so some y naughts basically. So note that these are not derivatives, but these are just two terms to indicate it. Okay, so these are some numbers. So you can see clearly that for this is a generalization. Yeah, generalization to nth order linear ordinary differential equation. Okay, so short. So now let's look at an example. So example, let us consider ty triple prime plus sine t of y prime, y double prime, plus 3y equals to cos t. Now note that this is a what? A third order linear ordinary differential equation. Yeah, we can basically, ordinary is redundant in the here because we are the most, all of the problems we are dealing in this course is ordinary, right? So now so you're given this with y of 1 equals to 0, y prime of 1 equals to 0, and y double prime of 1 equals to 1. Yeah, so you need to give, so third order means 3 initial conditions should be given to you, right? Third order conditions must be given. Okay, so let's work on this. What is the problem? So we want to see where does this has, so the question is, where does this, on which interval does it has a unique solution? Yeah, so we want to apply the existence and uniqueness. So first, put it in standard form. So when we put it in standard form, so that means we have to divide throughout by t because the coefficient of y triple prime should be 1. So y triple prime plus sine t by t plus 3 by ty equals to cos t by t. Yeah, so here this is your p1, right? So this is your So P1, this is your P2, and this is your G of T, right? So we have, so these functions, these functions are continuous. P1, P2, P3, sorry, G are continuous on, so the denominator is a problem which becomes 0. So if you remove 0, you'll get on minus infinity to 0 and 0 to infinity. However, since t equals to 1 belongs to 0 to infinity, the I is where the unique solution exists. This is the story again. So this is a straightforward generalization of what you had for function sorry, you had a second order linear differential equation. Okay, so let's move ahead. Now, there is, we want to discuss about the same thing about the homogeneous and the non-homogeneous part. So what you have is the following. So if you basically let g of t equals to 0 here, you will get a homogeneous differential equation. So if you put this to be 0, p1 t minus 1 derivative of t all the way until dot pn. So this is a homogeneous solution and has, and suppose general solution is given by yc, then yc will be given as a linear combination of n solutions which you get. So first of all, these will have, so this homogeneous has n solutions, say y1 to yn. Then we get any linear combination is also a solution. That is because of the superimposition principle. So we have that yt equals to c1 y1 plus c2 y2 until cn yn is also a solution. All right, and the proof will involve basically repeating the proof you had for second order differential equation. Yeah, take n derivatives and substitute in this equation here, and you can check that it's a solution. Now, these solutions form a fundamental set if the Wronskian is non-zero. So we have the following for y of t, which is c1 y1 t plus c2 y2 t dot 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 cn yn t to satisfy the n conditions, the n initial conditions, n initial conditions, this will give us what? If you make it satisfy the n initial condition, you will get n equations, n unknowns. So there's a unique solution. So we are trying to solve for C1, C2, C3, Cn, right? Because we are saying, well, any solution y of t can be written as a linear combination of these n solutions, which are linearly independent. So there is a unique solution, C1 to Cn, if and only if the Wronskian is non-zero for some t naught belonging to I. And in that case, what? In that case, y1 is a fundamental set. Mental. So the idea is very similar. We need Wronskian as well here to determine if the set of solutions are fundamental. Why do we need fundamental set of solution? Because then any solution can be written as a linear combination of these fundamental set of solutions. So what will the Wronskian look like? So if we generalize it, Wronskian looks like y1 So what is the Wronskian of n independent solutions? So let me write that down here. So how does Wronskian of y1 to yn looks like? So this is straightforward generalization of Wronskian of two solutions. So you take y1, you took y1 prime, but you keep on doing this until you hit y1 and minus one derivative of that. Similarly, y2 prime, y2 and minus one derivative of this. Then you have yn, you have yn prime, you have yn and n minus one derivative of this. This is your Wronskian. Okay, and the notation is similar. It's basically given by this is given by yn. Okay, so this is how you write down the Wronskian. Okay, all right. So again, if you look at theorem 4.1.3, it tells you the following. If y1 to yn are fundamental set of solutions, are fundamental, this implies y1, y2, yn are linearly independent, and other way around too. So it's fundamental, then these are linearly independent. If these are linearly independent, you have a fundamental set of solutions. But note, you need n fundamental solutions, sorry, n set of fundamental solutions, n set of linearly independent solutions to give you the fundamental set of solutions. So compare with this with the idea of the bases for the vector space. Here you are generating the null space of your differential equation, right? So now non-constant, so we will deal with mostly with constant coefficients. For non-constant coefficients, typically it's difficult in general, but typically numerical methods are used. Typically numerical methods are used. And or you can use series method, which we'll see later on. So you'll see series method. What kind of series? What do I mean by series? Power series methods. We'll see later. All right. So now we'll try to focus on an nth order homogeneous differential equation with constant coefficients. Means what? Means all these functions are going to be constant functions. So that means what? A0, A1, blah, 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 are real constants. So now how do we solve this? Nth order homogeneous differential equation with constant coefficient. So let's go back to what we did in the second in function of two for the second order differential equation with constant coefficient. So suppose you had a y double prime plus b y prime plus cy equals to 0. You postulated the solution to be of form y equals to e to the rt. You got ar square plus br plus c equals to 0. This was your characteristic equation. You solved this guy, this quadratic equation, and based on what kind of roots it had, whether it was real, distinct, real, but same, or complex roots, we had different scenarios. So this situation will be exactly the same. So we'll start with postulating y equals to e to the rt as a solution for some suitable r. We'll get a characteristic equation. We'll find the roots with the real and distinct roots, real repeated roots, and complex roots separately. So when I put basically A equals to RT, the differential equation basically reduces down to A0 R to the power n plus A1 R to the n minus 1 dot 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 A n minus R plus A0 equals to 0. This is the characteristic equation. Now, this characteristic equation is the equation with coefficients, real coefficients. And this equation can be written as a product of linear factors over complex numbers. Yeah, set of complex. So if you take any polynomial over real numbers, you can find the roots in complex numbers. Okay. So if we have the following, if we have all the roots are distinct with Ri belonging to R, then what are the solutions? So the solution will be e to the power R1t, e to the power R2t, dot, 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 e to the power Rnt. And this solution will form a fundamental set of solution. Okay. Now, similarly, if we had complex roots of polynomial with real coefficient occur, complex roots always occur in conjugate pairs. So what do I mean by that? If a plus I mu is a solution to a polynomial with real coefficients, then a minus I mu is also going to be the solution. Okay. Right. Now, if none of these are repeated, then the two corresponding terms in general solution will look like what? So if you have none of these repeat, then you will have e to the power lambda 1t cos of mu t, e to the power lambda 2t sine of mu t. This corresponds to lambda 1. this will correspond to one real root of one real root. Okay, sorry, to a pair of complex roots, right? A plus lambda I mu, lambda plus I mu, lambda minus I mu give this two set of solution, right? We have already discussed this in the case of second order homogeneous differential equation. Similarly, for next root, we'll have e to the power. So if we have lambda 1, mu 1, and suppose you have also lambda 2, mu 2, then you will have for every complex part, so mu 1, mu 2, e to the power lambda 2t sine of mu t. So these are the solutions, and there are how many of these? So since they appear in pair, there are 2, 4, 6, etc. of these, depending on degree. Depending on degree. Yeah, so these are so we are discussing the similarity. Now, suppose next case, if we have real repeated roots. So if r equals to r1 is repeated s times, that is, if multiplicity is s, as a root of, let's call this as a polynomial, right? I mean, like p of r, or maybe let's call this as c of r. If c of r, the characteristic equation is s, then we'll have y, we'll have e to the power r1t, e to the power r2t times t, e to the power r1, my bad, r1t, because the root is repeated. So r1t, t to the power t square to the power r1t dot 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 t to the power s minus 1 e to the power r1t. So the idea is you multiply with t, and how many times? If the multiplicity is s, you multiply by ts minus 1. So you multiply with t square, and then all these will form a solution. Now, repeated complex roots. So this is a difference, right? We haven't seen this before. Why? Because this does not happens when n equals to 2, right? Because complex root comes in pairs. There was only room for one complex roots, right? One pair of complex roots. So now, but this will occur if your differential equation is of higher order. So if r equals to lambda plus I mu plus or minus is repeated with multiplicity s, then we will get what? We'll get 2s terms. So 2s terms will be, so take e to the power lambda t cos mu t, e to the power lambda t sine mu t. So this is for the first repetition. For the second repetition, you'll have e to the lambda t cos mu t, e to the power lambda t sine mu t multiplied by another t. Okay, and then you keep on doing this, and you'll get t to the power s minus 1 e to the power lambda t cos mu t, t to the power s minus 1 e to the power lambda t sine of mu t. So the question is to multiply by t or not. So 2t or not to t? That is a question. Yeah, is the question. Is the question. Now, there are further difficulties basically in finding the roots. Hmm. What do I mean by that? Here, when you had second order, this equation was quadratic. And it's easy to find the roots of quadratic equations, right? You have to use quadratic formula. For cubic, there are Cardano's method, but again, it becomes cubic, it becomes difficult. And third order is difficult. And it's for fourth order, you can't even solve it using radicals. You can't solve quintic polynomials using radicals. That's a Galois. That's the consequence of the Galois theory. I mean, that is part, you can prove it using Galois theory. So how would we find the solution? So, well, one way is to guess the roots, try r equals to 0, 1, plus minus 1. Generally, we are solving the problems where we'll have a simpler form. Also notice if the characteristic equation is of simpler form, that means it's a polynomial in R square. Say, for example, if you have r to the 4 plus 5r square plus 6 equals to 0, you can basically replace r with something else, r square with something else. You'll see that you'll factorize like a, yeah, plus 2 equals to 0. So r equals to plus or minus root 3i, r equals to plus or minus root 2i, right? So this is how you can solve. But in general, it may be slightly hard to solve them. But again, we'll focus on the ones which are doable in our course. So let's look at the first one. So solve the y double prime minus, sorry, y, fourth derivative of y minus 5y double prime plus 4y equals to 0. So first things first, I'm going to use a short notation for this characteristic equation. So that is going to be r to the 4 minus 5r square plus 4 equals to 0. Now, it's a polynomial of degree 4, but it's actually like a quadratic, really, if you think about r square. So this gives me, I can factorize it or use quadratic formula on r square, not r. We can clearly see, I can see the factorization is going to be r square minus 4 times r square minus 1 equals to 0. So this gives me r equals to plus or minus 2, r equals to plus or minus 1. So real roots, all distinct, right? Real roots, all distinct. So therefore, solution is, what are the solutions? So y of t, this is a general solution, by the way, right? So we should say general solution is c1 y1, which is e to the power, say, 2t plus c2 e to the power minus 2t plus c1 e to the power t. Sorry, we should use something else, c3 and c4 e to the power minus t. So this is how a general solution will look like. And of course, if you want to find out, so c1, c2, c3, c4 will depend on your initial condition. Okay. So let's look at the part B. It says solve the same with the 4 initial condition given to us. So now we need to solve this. So B, so same as above D, the same as above differential equation, but with what? With initial conditions, right? So with initial conditions. So let's solve this one. So we are given y of 0. Y of 0. On one hand, it is given to you as 0. On other hand, you will get C1 plus C2 plus C3 plus C4. Then y prime of 0. On one hand, it's given to you as 0. Okay, that is also 0. What is the derivative of this though? So you will see that derivative of this is going to be C1 times, so we'll get 2C1 minus 2c2 plus c3 plus c4. That is also 0. Now, what is y double prime? So if you take y double prime, so y double prime of 0 is also 0. And if I take derivative here, I'll see that derivative of this is going to be, second derivative of this is going to be 4c1 plus 4c2 plus c3 plus c4 is also 0. And then I'll get y triple prime of 0 is, on one hand, it's given to me as 12. And on the other hand, I'll get what? So 2 times again, so 8c1 minus 8c2 plus c3 plus c4 equals to this. So this is 4 equations and 4 unknown. So I solve it. And when I solve it, I get the following. I will get So sorry, I made a mistake here. This should be minus, this should be plus, and this should be minus, right? Because we are looking at the derivative of this part. The derivatives will basically oscillate with plus or minus sign. Now I can work on this, solving this using some matrix method of Gaussian elimination, or I can basically do the same thing here. So if I use the Gaussian elimination, you can see that you will find that C1 equals to 1, C2 equals to -1, C3 equals to -2, and C4 equals to 2. So these are the solutions to your, so what do you get? You therefore your yt is going to be C1, which is e to the power 2t, minus 2, sorry, minus C2, which is -1, so e to the power minus 2t plus C3, which is going to be minus 2 e to the power t. C4 is plus e to the power t. So this is your solution. All right. So you should be able to solve this system of linear equations. If not, we'll do it. I'll post the written up solution of that. All right. So now let's deal with the next one, which is D. Or let's start with C. C is left out too. So C is y triple prime. So what is the characteristic equation in this case? Is going to be r cubed plus r square minus 2r equals to 0. Now, if you look at this equation, so we need to solve this equation. Here, by inspection, you can see, so we can pull out what this should be r, because there's not just y, not y prime, right? So you can observe that 1 is a solution for this one. So let's factorize r minus 1 out of it using long division, or you can do the following: r cubed minus 1 plus r square minus 1 equals to 0. So this will be r minus 1 times r square plus r plus 1, and r minus 1 times r plus 1 equals to 0. So this gives me r minus 1 times r square plus 2r. So if we do this, you get r square plus 2r and then I'm taking what common here? I'm taking, so I get another r plus 1. And there's another r square plus 2r plus 2 equals to 0. So therefore r equals to 1, or now this is going to be, this is an irreducible. So let's use quadratic formula to we get r2 and r3 are given by -2 plus or minus b squared minus 4ac. That is going to be plus or minus 2i divided by 2, which is going to be -1 plus or minus I. So one is R3, the other one is R4. So corresponding to this root, we'll get yt equals to, so corresponding to this part here, we'll get y1, sorry, constant times e to the power rt, which is t. Corresponding to these two guys, we'll have complex roots. So we'll have, so first will be c2 e to the power, now you have minus, so lambda is -1, mu is 1, so we get e to the power minus t cos t plus c2 e to the power minus t sine t. So c2, and then next with constant should be c3. So this is a solution for this. Now let's look at D. So D has, so let me write down the characteristic equation. So y, what do I get? I get r cubed plus r square minus 5r plus 3 equals to 0. Now again, this is a cubic polynomial. In general, cubic polynomials are hard to solve. Let's see by inspection if we can find any root. And you can clearly see if r is 1, so r is 1 is a root, right, by inspection. So we should be able to divide by r. So if you pull out r minus 1, so we should be able to divide by r minus 1. So when you take r minus 1 common, what is left in the bracket after the long division is r squared plus 2r minus 3 equals to 0. This again has a factorization as r minus 1 times r plus 3, r minus 1 times r plus 3. So we get r minus 1 times r minus 1 times r plus 3 equals to 0. So here what happens? Real repeated roots, right, for this part. So our solution will be y of t equals to c1. Now corresponding to the first one, it will be e to the power t. Now, since this root got repeated, and how many times did it get repeated? Twice, so it will be 2 e to the power t times e to the power t. If it was repeated, say another r minus 1, then it will be another t, which will be make it t square. But since it's only repeated twice, we get that part. So for this part, we got this as a root. Now for this part here, we'll get e to the power minus 3t multiplied by some other constant, say c3 plus c3. So again, you see the different ways your characteristic equation splits, you're getting different roots. So let's look at E now, problem E, where we have what? We have y to the 4 plus 6y double prime plus 9y equals to 0. So characteristic equation is r to the power 4, 6r square plus 9 equals to 0. This gives us what? This is same as r square plus 3 the whole square. This gives me what? R equals to plus or minus root 3i, but with what? Each is multiplicity 2. So each with multiplicity 2, or we call this as double root 2. So therefore, what will be the roots? We'll get y of t equals to. So note that we consider first root will be root t. So we'll consider root 3t, so root 3I and minus root 3I. So corresponding to these two guys, we'll have the first part of the root written out here, which is going to be C1 again. There's no real part here, so it will be cos of root 3t plus C2 sine of root 3t. So this is because of this being the root, all right? Now, due to the fact of double root, due to the fact of multiplicity 2, because of this part, we'll get, again, C3. What you have to do is multiply by t. So t cos root 3t plus C4t sine root 3t. So this is the general solution of this. So until now, so what have we done so far? We have discussed the homogeneous linear differential equation with the constant coefficients. Okay, and we have solved them using characteristic equation. We have seen what happens when the roots are of different kind. What you mean by different kind? A root either can basically appear once, twice, all right? And also depending on whether it's complex or real, we have seen this. Okay. So now next case is about finding the particular solution. So we want to still copy over the methods we had for second order non-homogeneous linear differential equation, again with constant coefficients. Do this here. So what is the non-homogeneous? So non-homogeneous part is basically bringing this to be non-zero. That gives you the non-homogeneous. So we'll use the method of undetermined coefficients whenever GT is of form polynomial, exponential, sine or cosine, or sum or product of these functions. We'll use method of variation of parameters, which can also extend to an order d. In this case, whenever the differential equation does not has constant coefficients or RHS is not a polynomial, exponential, sine, cosine, or product hereafter. Okay. So we'll use this. This is a similarity. So this is what we do, right? We can copy the second order differential equation, what we did in second order differential equation, when we could apply the undetermined coefficient right away the same way to nth order linear differential equation when we can apply the method of undetermined coefficient. And what do we mean by we can apply the method of undetermined coefficients? When these guys are constants, so the coefficients are constant and g of t is of special form, either exponential, polynomial, sine, cosine, and or multiple or sum of these. Now, what is the difference between these two methods, right? What is the difference between second order and nth order? The roots of characteristic equation may have multiplicity greater than 2. That means we need a higher power of t for our proposed form of yp. Okay. So let's do an example first. So example 1, you have y3, so third derivative of y plus 3 times second derivative of y plus 3y prime plus y equals to e to the power t. Again, always the first step is to find the characteristic equation and see what do we get as a solution of characteristic equation. So we get characteristic equation as a form r cubed plus 3r squared plus 3r plus 1 equals to 0. Now this looks exactly like as r plus 1 to the power what? 3 equals to 0. So r is the repeated root. So r equals to minus 1 is a root of multiplicity t 3. So what will be the complementary solution in this case? It will be, first will be c1 e to the power minus t. Second one will be c2 t times e to the minus t plus c3 t square e to the power minus t. So this is the solution to the homogeneous part. Now, for yp, we have to take e to the power minus t and multiply it by some coefficient here. Yeah. And this coefficient is how many times is a minus 1 root of this? So minus 1 is a root, it's a triple root, so it is going to be t cube times e to the power minus t. In general, it is t to the power s, right? And only we get t cube because of the overlap of root, because minus, this is e to the power minus r t as well. If it was 2 e to the power 2t, then you didn't have to multiply by any power of t, right? Okay, so now let's solve for this. So substitute in differential equation. So if you substitute this in differential equation, you put it in this equation. So now you need a coefficient for this. So let's say a times this. So substitute in this and you will find, so find yp would be actually 1 over 6. Let's say easy exercise, you should do it. That you'll get yp equals to 1 over, sorry, you'll get a equals to 1 over 6. So this will give you yp to be 1 by 6 t cube e to the power minus t. So this is your yp. And if you want to write the general solution, because it says when it says solve, you have to write the general solution. This implies y equals to complementary plus particular, which is going to be c1 e to the power minus t plus c2 e to the power t to the power minus t plus c3 t square e to the power minus t plus c. There's no constant for yp, so it's going to be 1 by 6 t cube e to the power minus t. So this is your solution y. Okay. Now let's look at the next problem. We have find yp, which is going to be 4y double prime plus 2y double triple prime plus 5y double prime equals to 3t plus 2t e to the minus t e to the power minus 2t. So we are interested in what will be the form of yp. Again, yp is decided by what are the solutions here, right? If there's an overlap or not. And then you basically go and look at this part. So let's embark on that. B. So first we need to find characteristic equation for the homogeneous part, and then see if there is any overlap. Homogeneous part, we get what? We get r to the power 4 plus 2r cube plus 5r square equals to 0. This gives us what? R square times r square plus 2r plus 5 equals to 0. This gives me what? R equals to 0 of multiplicity 2. Then what do I get? And R equals to, this is a complex, this will have complex roots. You can see that it's going to be minus 1 plus or minus 2i. So in this case, we'll get, this will correspond to C1 e to the power 0t, which is C1, and what we'll get? C2 times t e to the power 0t, which is what? C2t. This will give us C3 e to the power minus t times cos 2t, C4 e to the power minus 2t sine 2t. Now that you have found out those roots, so sorry, those solutions to the homogeneous part, now you have to see are they repeated in the particular part, in the non-homogeneous part, so that we can decide what to do about it. So here is the problem. So is there an overlap? And the answer is yes, there is an overlap. Where is the overlap? Overlap corresponds to, so overlap is corresponding to here. Yeah. So this, there is no overlap here because no e to the power minus t comes with a t here, right? And for this guy, there is also an overlap with this one. So what shall we do? So our yp will have the following form. So for the forms which has an overlap, the first part, 3t. So we need to multiply. So for 3t, corresponding to 3t, we'll have at plus bt. Now, because of, so that is corresponding to polynomial of degree 1, you will have a linear. Now you have to multiply by how many times 0 became the root of yp. It became 2 times, right? So 0 was root of multiplicity 2. So this gives me, I should multiply by t squared. So this came because of what? Because of, so what? Because of 3t in gt, yeah, as a sum. This came because of repetition of roots, right? 0 as repeated roots. Okay, it's twice repeated. So that is why we get that part. Now, what about the next part? If you look at 2t e to the minus t, it's not there here, right? One may say, well, e to the minus t is here, but no, it comes with sine or cosine, not with t. So you will get, for 2t, you will get, corresponding to 2t, you will get c plus dt e to the power minus t. And this contribution is because of, for since what 2t appears in g of t. So 2t e to the power minus t appears, right? Now for the third part, the contribution will be e to the power minus t sine 2t. Now does that appears here? Yes, it does as a solution. So now this will add up. This will become, how many times does it appear? It appears once as a root. So we get t e to the power. So you multiply by t e to the power minus t times c. So c is already taken. D cos t is also taken. F sine 2t plus g cos 2t. So this tells you how the form of the should look like. All right, folks, that's it for today. Thank you for your attention.